Okay, I hope this time everything is being recorded. So I guess my screen is visible here, yeah, right? Well, yeah, as long as the recording is going on, let's start out. So welcome everybody to my next video. Today I'm recording a brand new video to explain the theme called Simple Demo. So we're going to be taking a look at this Java code, and I will be explaining this for you. Yeah? So in total, we here have like over 200 lines of codes, and yeah, like when I run this program, I just imported it from like Moodle, and when I run this program, uh, this is the result that I get. Yeah. So when I run this, every time I run this, I get different values. Yeah, random like different generations, and like fittest version is also going to change. I will show you it quickly, and then we're gonna go into like how the code works here. Yeah? But yeah, like running process is taking a little bit of more time, but it should be fine. 1 second. Anyways, like while I guess it's gonna take too much time. No, it's not. So I'm sorry for it taking a lot of time because my machine is not the best. But here we have it. As you can see, like last time we were having 2 generations. Now we have like many generations, as you can see. So I will explain the code in detail for you now. We're going to take a look at why we are getting such result. Yep. Anyways, yeah, starting from line 1, we are just importing Java code just like usual to assign a random value. Yeah. And then moving on, we are just leaving like blank space. Then we are like, it's just for readability. From the line 3, we are starting out the main code. Like this is this one is just a comment to explain what kind of code we are going to write. And then we are here specifying the class, right? Public class simple demo get. This actually, oh, when I type this class when I touch it twice, it's running the problem. I don't know why, but here we are specifying the class, and here we are opening the main class called simple demo J. Yeah? Simple demo GA, and this class actually controls the genetic algorithm steps. Like previously on in genetic Java program, we have also discussed there we weren't specifying a demo GA, yeah, but here we are doing it, so you need to pay attention for this one. Moving on, on line 6 here you can see that we are specifying population. Yeah, so here we create a population object. Yeah, we have talked about objects, so you might probably know what objects are already. This here stores and holds an array of individuals and manage fitness calculations. Yeah, here it's gonna manage fitness calculations. Then we are also specifying like the fittest individual fittest. Here we are like, we are creating a variable here that will store selected best individual from the population. So it means like whoever is the fittest, it's gonna select by this code. Yep. Second fittest, as you can see, you might get the idea already. It's gonna select second best individual on the program. These two act as a like as parents, like as the parents for crossovers. And then int generation count 0. What does this line of code mean? It means we are tracking how many generations have already passed. Yeah? And it's starting from 0 here. So you need to pay attention to this. Moving on line 10 for readability, we are just moving it as blank here. And then public static main void, we are just starting out just like in older programs. Static main void, do you remember that code? Like we used to use it all the time, like static void merge sort, just like in the other program. Yeah, so here public static main void this is the entry point of our program. Execution actually starts from here. So yeah, here we are starting out the execution process. And then we are simplifying here. We are actually randomizing things. Yeah, random. We are creating random object, and here random object is being created in the method. Yeah, in the main method. We will use it as like mutation probability and check it later. Yeah. Okay, simple demo. This code, we are creating an instance of the main GA controller class. So later we can call its methods like selection over mutation. Yeah. Okay. We are here initializing the population value. Yeah. This line of code here is initializing the population, and how we are doing it, the code here creates like 10 random individuals. Yeah, because size is 10, so we are creating a random 10 individuals, and each individual has 5 genes, and each gene is 0 or 1. So there are two possible values, either 0 or 1, and we are moving on like that. Yeah. We are also calculating their fitness level a little bit later. Yeah, who is like the fittest. Yeah, calculating fitness individual. Yeah, demo population, we are like calculating their fitness level. Then a little bit later, like generation, here it's presenting like, yeah, printing out the code. This is like output of it. Yeah, generation, and it's gonna generate who is the fittest. We are using plus operator. We are going to combine generation with the fittest people. Demo.generation count, it's gonna, yeah, pull up that code, yeah, and it's gonna combine them together and print out as the result. Well, it prints out the generation 0. For example, you might see generation a code like here you might see in the output generation 0 and fittest 4, but it always can be like different object here, like I did here. I did so, but it might be different numbers, so next time it could be a different number. Anyways, we are using the while operator here just like usual. We had while operator in like older programs too, as you can see from merge and insertion sort. You remember what while does. So what what essentially does is that we keep looping until we find the best possible fitness. Yeah, and as long as the value is going to be less than 5, we are getting this fittest population. Yeah, so it is going like that. And then here a little bit later, so okay, where is 111? Okay, let me get this straight. Okay, if you like, I can give an example here. If you think of like a genes as 5 light switches, imagine there are like 5 light switches, and A1s here means switch on, and fitness is simply how many switches are on. The goal is all 5 on. Yeah, so if we have like 3 switches, it's 3 switches on. So it's like this. As long as it's less than 5, it's gonna keep running. Yeah. Anyways, so demo generation count here, this line means like each loop iteration is one new generation, so we increment the generation counter. It's like with this code we are incrementing the generation counter as we go along. We are doing like crossover here, demo.crossover, and then a little bit later we should be like doing, yeah, here we are doing crossover. Then there is also like mutation probability. This line of code, this is a probability check. This line is a probability check, so if it passes, we mutate. Here one important detail you need to understand is next ln, next int here, next int can be negative. Yeah, so here %7 here can be negative too, which slightly changes the probability in practice, but for a demo it still behaves like mutation often. Yeah, so yeah, demo mutation, as long as the condition is true, we mutate by flipping one random bit in each of the 2 parents. Yeah, so this is what the demo mutation does here. Yeah, closing the bracket. Then here on the 41 no, here we are calling offsprings, right? Then we are population calculating like the fitness level of population, yeah, as you remember. Starting out system generation, fittest population, it just prints the progress for the current generation, yeah, how it's going on, yeah. uh, I need to actually do this. Rest out this one, yeah. So now it should be fine, yeah. I hope well, system out println, again we are going in, yeah. This is like printing out, this code is like printing out when a solution is found and in which generation like the solution is gonna be found, yeah. Well, we are also printing out the fitness of fittest people in generation, yeah. Fitness level of get fittest here means like we are pulling off like the fittest population from like from a little bit we are just referring to the old code we wrote here, yeah. And yeah, here we are creating a for loop. As long as the loop is gonna be like loop's value is gonna be less than 5, it will keep printing it out, yeah. So it should work like that. Loop through the 5 genes, yeah, 5 genes here, 5 genes in the fittest individual, yeah. Okay, well, print here we are printing out each gene value. That's why the output appears like 1111, yeah. Here we are ending our loop and moving on into selection side, yeah. Well, we now define like GA selection method, yeah. So in our demo GA program we are specifying GA selection method here. Well, we are as usual starting out with void selection. This opens the selection method, and then as we go along, we are picking the best individual here, yeah, the fittest individual. Just like usual, fittest individual is being like taken out of them. Fittest equals population times get fittest, not times like dot get fittest. This is like calling population get fittest, which returns a clone value of the best individual here, yeah. And as we go along, select the second. We are also selecting the most like second fittest individual, just like usual, yeah. It is returning clone best value, yeah. It's important to understand here that it's a clone best value, not the original value. So clone best value is being referred to the second one, yeah. And yeah, as we are going along, void crossover, here we are specifying void here we are opening crossover method here, yeah. Void crossover method. So we are using like as usual the random operator. So creating a random operator here for this method, it will cross over points. So it will make the points crossover, yeah. And here we are starting mixing things up, right? In selection we are starting to mix things up. We are picking in here we are picking such individuals from a specific, very specific range. We are picking an integer from 0 to gene length 1, yeah. And gene length is 5, so the crossover point is 0.4. So it's like that. Well, if crossover point is gonna be 2, the indice is going to be 0, and because one loop below runs crossover point, yeah. Okay. We are swapping values among parents here. It means like exchanging the genes between the two selected parents, yeah. Using the for operator just like usual. For loop here, what it essentially does is that while the loop is 0, it crosses up to crossover point 1, yeah. Okay. And here we are starting out mutation already. Yeah, the next method with us is going to be mutation method. So void mutation, open mutation. We are opening the mutation method and creating a random generator for mutation points. Like here earlier we have created a random generator too. Yeah, I mean with all the methods we are creating here, we are randomly creating random ones, and here yeah we are doing that again. Yeah, we are creating new random method, and while we are creating this, it's important to understand that we are selecting a random mutation number, like point. Yeah, to be more specific, it's point, not number. We are here picking a number that is 0.4. Yeah, it means population times individuals times like generation length. It's very specific, so you want to pay attention here. If the selected gene is gonna be equal to 0, it's going to be the fittest individual. Yeah, so as you know, like there is a difference between uh, this sign and that sign. It is just like giving out one value, and the second is like making it equal to that value. Yeah, okay, yeah. If operator, if it's gonna be equal to 0, then it's gonna be like the fittest, and set it to 1. Yeah, fittest gene is being set to 1, otherwise it's gonna be set into 0 value. Yeah, the value of it is going to be 0, and we are ending the ending our method in here. Well, new mutation point is being started out, so here we are picking a new mutation point again, 0.4 for second fittest value. Yeah, it is for second fittest value. If second fittest has 0 at that index, we are going to flip it to 1. Yeah, first value. Otherwise it's gonna be flipping into 0 value again. So we are playing between 0 and 1. Yeah, if it's gonna be 0, it's gonna be printing out. Otherwise it's gonna be if it's gonna be 1, then it's gonna be 0. So yeah, working out like this. Yeah, and we are ending the loop here. Yeah, and we are ending the mutation. So okay, hold on, we are getting offspring, so we are choosing which two of the method modified parents is better after crossover mutation. So get fittest offspring, or yeah, basically the usage of it. We are opening, yeah. We are opening get fittest method here. Get the get the offspring method here is being taken out. Sorry. Then if fittest individual is going to have higher fitness level than the second one, it's gonna return the fitness level. Yeah, it's like end of the branch. Otherwise it's gonna return like the offspring of it, right? Yeah. And moving on to the 119 line. So next we are inserting the best offspring into the population, right? Into the like the best, adding fitness offspring to the population. So essentially what we are doing here is that we are calculating like the fitness for fittest after crossover and mutation. Yeah, after using crossover and mutation method, we are calculating who is going to be the fittest here. When we are calculating for second fittest after crossover method, we are also finding the worst. Here it's like least fit individual. Yeah, so we are essentially finding the worst individual in the population array in here, and this is returning the index of the individual with smallest fitness. And yeah, wait, sorry. Okay, accidentally pressed the wrong button. But here we are starting out from the class again. Yeah, after ending the offspring method here we have ended like the offspring method, yeah, this method, and we are starting out individually from the class again. So what we are doing in the class, we are defining individual which represents one candidate solution. It's like opening one individual class. Oh, sorry, it's opening one individual class and implementing clonable, so we can return clones in population methods. Okay, int fitness equals 0, storing the fitness score for the individual, what we are doing here, and then we are giving out value, the chromosome. Yeah, it's like chromosome, 5 genes, and each one is going to be either 0 and 1 or 1. Yeah, just like we have discussed it like previously, it's going to be very similar to that one. Gene length is going to be 5. It's going to be used for random bounds. Well, calling out the public individual, what it is doing here is it's a constructor, as you know. Yep, this constructor runs whenever we create a new individual. So randomizing things a bit, as usual, random use it for initializing genes. We are initializing genes again, and then we are also filling out values with the random genes. Yeah, next we will fill genes with randomly. Yeah, and we are using the for loop again. Loop here takes a look across 5 genes. That is like yeah. So it's gonna take a look at 5 genes, and using a new function in here, abs. It means like this line of code like sets genes into 0 or 1, and then it's going to give either 0 or 1, or sometimes it also can give -1. So abc here, abc function fixes it to 0 or 1, so -1 doesn't get printed out because of this one. We are ending like initialization of this loop. Okay, and calculating fitness level again. Yeah. So yeah, with this one, uh, the fitness when the fitness level is gonna be equal to 0, it will be computed later by calculation fitness program that we are going to talk about later. Yeah, this calc fitness program. Well, as you can see, we are starting out from public void again. Yeah, so we are opening calculation fitness method, calc fitness method. Yeah, when fitness is set 0, it's going to reset like fitness to 0 before counting. So we are, before starting out like the counting, we are setting it to 0. Then we are using the for loop. Loop again looks across 5 gene positions. This is using 5 directly, and important thing here to pay attention is that it's going to be the same length as gene length, right? It's going to be the same length with that one. And yeah, we are incrementing fitness and ending the line, also ending the loop, overriding it. So yeah, override annotation here. We override the clone from object, right? When we are opening clone method, it can throw clone not supported exception. So when we are making a shallow clone using super clone and cast it to individual, we are creating a new genes. Yeah, we are creating a new genes that will be new genes array, so the clone has its own copy, like the deep copy of it, right? And loop is going to be through all the gene indices. Then on line 171, we are going to copy each gene from the each original site into the clone, right? Into the clone, and ending the loop right here. So this is the end of clone, end of individual class. Yeah. here we are ending the clone, and then we are ending the class itself. Yeah, here we started the class, as you remember, and we are finishing the class right right here after override. Yeah, so next we're gonna discuss about population class. It holds the set of individuals. Well, when we are opening population class, we are just making the variable size equal to 10. What does it mean? In this file, the array is gonna be also fixed at 10. Yeah, the value of array is gonna be 10. It means it will pop out like 10 individuals, and this is going to hold the best fitness value found in the population, right? So here it's gonna pop up like the fittest guy right here from the population itself. Starting out with initialization again. So it is like comment method for filling the array with new individuals. We are just opening and initializing population again. So the parameter size here, yep, parameter size in here is gonna be like exiting, but the method here uses same individual lengths, so the array size stays the same, yeah, as 10. So array size and the value here, individual value, both of them are 10. Public main void, creating a random individual for each slot, right? And right after that, creating a random individual for each slot using like the for function, like as long as this value is gonna be less than individual's length, it's gonna keep being printed. And we are yeah, we are terminating no, like we are just finishing that loop, ending this loop, and initializing new population loop. Wait, sorry, that's the iPhone. Method to locate the best individual. So we are locating the first, we are starting out by opening the get fittest method, and then we are here using int max fit, so it is generating like the minimum value, and start max fit very small, so any real fitness will be bigger, right? And we are also tracking the index of the best fitness seen so far. uh, it will loop through the all individual, yeah, for int, yeah, again it will loop through the all individual length, and it's gonna identify the individual who has a fitness at least as large as max fit, yeah, it should be at least as large as max fit. So essentially this is what these lines of codes are doing, and we are ending the loop, and we are making the fittest individual equal to max fit index. So here it stores the best fitness value into the population, so it can find the field that is fittest. Okay. uh, Try, we are here using a new operator like try, and try here starts out by blocking for cloning, and it's returning like a clone of the fittest individual from max fit index, right? If cloning here fails, then it catches the exception from this line, right? If it's gonna fail, it's gonna catch the exception method. And ePrint stack trace is starting out. It's printing the trace for debugging. Yeah, we are debugging it and returning null at the end. If cloning fails, it's gonna return null at the end. So this is essentially what it is doing. Yeah, again, opening get second fittest, and int max fit 1 is equal to 0. What it means is that it's gonna store an index of the best individual, and second is gonna be second best, right? We have already talked about this. The first one is gonna be like the best guy. Second is gonna be like the runner-up, yes, second runner. Again, using the loop here, so it's gonna loop over all the individuals, and it's going to calculate if current individual is better than the current best. Is current individual better than the current best? It's gonna identify this, yeah. The old here becomes like the second best. Here, the old is becoming like the second best, and max fit is equaling to I. It means current one becomes new best. So old is gonna be second best, one becomes new best. Clear, I guess. And else if method, by this one, otherwise, it's just meaning like otherwise. If current individual is gonna be better than the current second best, it's gonna update second best. So, and we are ending it using a try cloning again, yeah, and catching the cloning exception. So, and on line 225, we are just printing stack trace and ending the catch. As you can see here, we started catch and we are ending the catch. So yeah, again, the same thing. We are starting out from the public index, and we are like min fit val. It is like minimum fitness value is very large, so any real fitness will be smaller than this one. We are also tracking down like the index of the minimum fitness and also looping across all the individuals. Then we are like, if the fitness level is going to be less than or equal to the current value, current minimum, it's going to update min fit val. Yeah, min fit val is going to be updated, and it's also going to be updating the index of it. Quickly returning like the minimum fitness value. Then here it's getting like the least possible value and computing it this fitness for the entire population. Yeah, here we are doing it for the entire population, like calculating it for the entire population. It's gonna loop through the individual again using the loop, yeah, and then it's gonna ask each and every single individual to compute its own fitness by counting once. Then again, it's going to update the population fitness value after recalculating all fitness values. And yeah, that's about it for today's program. Basically, we represented with you guys in today's program that each individual is a 5-bit string, like 10, like 10110. Yeah, as you know, like last year we have learned about like with light bulbs we have learned about like 1 and 0. If it's on, it's gonna be 1. If it's off, it's gonna be 0. So it's just like the fitness in like in conclusion, fitness is like the code that defines like fitness as number of ones. So 10110 is gonna be is gonna have a fitness of 3. We also use it like the selection method. Selection method, as you know, it could just picks 2 of the best individuals every time. So it is what it is doing. If for example, if it's like a crossover point is gonna be 2, parent A is gonna be 11001, and parent B is gonna be 00111. So it is swiping the indices between 0 and 1. Mutation is just the code that flips one random bit in each parent sometimes. And the termination stops when fitness reaches 5, which means genes are 1111. Yeah, 1 and 1. Replacement is just the code that replaces individual each generation ready state. So we're gonna be running the program one more time to see if we are gonna be getting a different output. So yeah, as you can see here, only one generation, and the fitness is gonna be 5, and solution find in the next one is gonna be a little bit different. So basically, this is what today's code is gonna be about. Yeah, thank you very much for attending, and thank you. Have a good day.